How do people decide how to allocate their time between paid work and time spent on other tasks? Let's consider an example. Max is a professional juggler. He finds that his total product is described by the function 21h minus h squared, where h is the total number of work hours per day. We could interpret the total product as the number of spectators who come to watch Max juggle. If each spectator donates $1, then his total product is the same as his earnings. We can then evaluate the trade-off between earnings and free time in order to determine the optimal number of work hours. What is Max's total product? Well, it's just 21 times h minus h squared. So for 0 hours, his total product is 21 times 0 minus 0 squared, which is 0. For 1 work hour, it's 21 times 1 minus 1 squared, or 20. For 2 work hours, it's 21 times 2 minus 2 squared, or 42 minus 4, which is 38. For 3 work hours, it's 21 times 3 minus 3 squared, or 63 minus 9, which is 54. And so on up through 10 work hours. What is Max's average product? It's just the total product divided by the number of hours worked. For 0 hours, you can't divide by 0, so the average product is undefined. For 1 work hour, average product is 20 divided by 1, or 20. For 2 work hours, it's the total product of 38 divided by 2, or 19, and so on up through 10 work hours. What is Max's marginal product? It's approximately the change in total product divided by the change in hours. However, in this case, the change in hours is always equal to 1, so his marginal product is really just approximately the change in total product. I'll go through the whole formula so that you can see what I'm talking about. For 0 hours, marginal product is undefined. For 1 hour, marginal product is the change in total product, 20 minus 0, divided by the change in hours, 1 minus 0. So 20 divided by 1 is 20. For 2 work hours, the marginal product is the change in total product, 38 minus 20, divided by the change in work hours, which is again 1. So 18 divided by 1 is 18. For 3 work hours, the marginal product is 54 minus 38, or 16, divided by 1, which is 16. And so you can see that all we're doing is taking the change in total product for each number of work hours. For example, at 4 work hours, the change in total product is 68 minus 54, or 14. For 5 work hours, the change is 80 minus 68, or 12, and so on up through 10 work hours. If we plot total product against hours worked, we get Max's production function. For 0 work hours, his total product is 0. For 10 work hours, his total product is 110. The production function is increasing at a decreasing rate, and it shows the values that are included in the table. We can also consider a geometrical interpretation of the average and marginal products looking at specific numbers of work hours. For example, when we have 4 work hours, the total product is 68. The average product is the slope of a ray from the origin through the point 468. The slope in this case is 17. It's just rise over run, where rise is 68 and run is 4. 68 divided by 4 is 17. Note that when we calculated the average product before, we just took the total product divided by work hours, which is 68 divided by 4, and we got 17. So the slope of a ray through the origin is the same as the average product. The marginal product is the slope of the production function at 4 work hours. We can see this by plotting the tangent line at 4 work hours, and the slope is approximately 14, which is the marginal product. When we have 8 work hours, the total product is 104. The slope of a ray from the origin through the point 8, 104 is 13, and that is the same as the average product. The slope of the production function, when we have work hours equal to 8, is approximately 6, and that's the marginal product. You might have noticed in the previous example that when we went from 4 work hours to 8 work hours, the average and marginal products both decreased. In fact, average and marginal products are steadily decreasing as work hours increase. You can see this by plotting average and marginal products in a graph, but you can also see it from the table. We said that the total product is increasing at a decreasing rate, and it's the decreasing marginal product that gives the decreasing rate. One more thing to note before we move on is that Max's production function is the mirror image of his feasible frontier. The feasible frontier is plotted with hours of free time on the horizontal axis instead of work hours. But work hours plus hours of free time must add up to 24 hours in a day. So we can use a formula to go back and forth between work hours and free time. For example, when we have 0 hours of work, we have 24 hours of free time. When we have 10 hours of work, we have 24 minus 10, or 14 hours of free time. We can plot the feasible frontier simply by running the production function in reverse. The feasible set is all possible combinations of total product and free time that are achievable. The slope of the production function, as we already said, is the marginal product. But note also that the slope of the feasible frontier is simply the negative of the slope of the production function. And the absolute value of the slope of the feasible frontier is the marginal rate of transformation. That means that for any given number of work hours, the marginal product is equal to the marginal rate of transformation. And we're going to use that fact in a minute when we look at the optimal number of work hours. We know that the optimal point will lie on the feasible frontier. But to find the optimal number of work hours, we also need to know something about Max's preferences over earnings and leisure. Suppose Max would only be willing to work another hour or to give up an additional hour of free time if he makes at least $16 in that hour. Then the marginal rate of substitution is $16. Max will only continue working as long as the marginal rate of transformation is greater than or equal to the marginal rate of substitution. In other words, he will only continue working as long as an additional hour of work produces at least as much value for him as an additional hour of free time. We can see this in a table where we have a constant marginal rate of substitution equal to $16, and where the marginal rate of transformation is the same as the marginal products we already calculated, except that now they're expressed in dollar terms because we said each spectator pays $1 so that the marginal product and the total product are both in dollar terms. Now we need to find the optimal number of work hours. So we can start by asking, would Max be willing to work 1 hour? Well, in the first hour, he makes $20, and the value of his free time is only 16, so yes. Would he be willing to work a second hour? In the second hour, he makes a little less, only $18, but it's still more than his value of free time. So yes, at 3 hours, he's only making exactly the same as his value of free time, but we say that he would work that hour. However, on the fourth hour, he would be making $14, which is less than the amount by which he values free time. So he's not willing to work the fourth hour. That means that he'll only work up until the point where the marginal rate of transformation equals the marginal rate of substitution, which in this example happens at 3 hours. Those are his optimal work hours. We can also see this by plotting it in a graph. Remember that the total product is the same as total earnings in this example, and Max's utility increases as he gets more total product and/or more hours of free time. An indifference curve shows all the combinations of total product and free time that give Max the same level of utility. And the slope of the indifference curve is the marginal rate of substitution. For higher indifference curves, we have higher levels of utility. So ideally, Max would like to achieve the highest possible indifference curve. Indifference curve 3 is not feasible because it doesn't touch Max's feasible set. Indifference curve 1 is achievable, but Max can do better. At point A, MRT is greater than MRS. At point B, MRT is less than MRS. Indifference curve 2 is the highest attainable indifference curve. That's where the indifference curve just barely touches Max's feasible set. At point C, MRT equals MRS. And remember that the slope of the feasible frontier is MRT, and the slope of the indifference curve is MRS. So the optimal point is where those two are equal. And that gives 21 hours of free time, which is the same as saying 3 hours of work, which is the same result we got by looking at a table. That means the optimal number of hours in this example is again 3 hours. What if Max's productivity doubles? Then we simply take the original formula for total product and multiply by 2. We also double the average product and the marginal product. So when productivity doubles, average product, marginal product, and total product all double. We can also see this in a table where total, average, and marginal products are all twice what they were originally. We could have also worked through all the procedures that we used originally to calculate total, average, and marginal products, but it would give the same result, and so multiplying all of the numbers by 2 is easier. We still assume that the marginal rate of substitution equals $16, and now we need to calculate the new optimal number of work hours, considering that productivity has doubled and the marginal product is now higher than it was before. So at the first work hour, Max will earn $40, which is well above the amount by which he values free time. So he will work the first hour, he'll also work the second hour, and so on. When he gets to the 7th hour, he's just indifferent between working that hour or not, but we'll say he works the 7th hour. However, when he gets to the 8th hour, he'll be making $12 if he works that hour, but he values his free time at $16. So it's not worth it for him to work the 8th hour. That means that Max will only work up until 7 hours, which is where the marginal rate of transformation equals the marginal rate of substitution. They're both 16. Finally, we need to ask about income and substitution effects. When productivity increases, the feasible frontier shifts outward, and there is more output for any given labor input. When that happens, we could either have an increase or a reduction in work hours. If work hours decrease, we say that the income effect dominated. Note that a decrease in work hours is the same as an increase in free time. If work hours increase, the substitution effect dominates. In this example, Max's productivity doubles, which allows him to reach a new higher indifference curve, representing a higher level of utility. And he also has a new optimal point, where instead of 3 hours, he's now working 7 hours. Because work hours increased and free time decreased, we know that in this case, the substitution effect dominated. Note that this outcome is different from the historical evolution of US productivity and work hours depicted in the textbook. In the United States, since the early 20th century, productivity has increased, but work hours have generally decreased on average. That may be due to differences in the indifference curves, which in turn reflect differences in preferences relative to those presented here. However, it may also be due to labor legislation, the activity of labor unions, and other factors which are not included in this model. So even though this model does not provide a complete description of all the factors affecting the decision of how many hours to work, it still is useful because it provides a simple and powerful tool for analyzing individual decision making. That is, we say that individuals optimize subject to constraints, or that they seek to achieve the highest utility level they can within their feasible set.